Good morning or good afternoon, ladies and gentlemen. My name is Mattia Busana. I am doctor at the Medical University Center of Göttingen, and today we talk about a very interesting topic for me, that is the physiology and pathophysiology of ECMO or extracorporeal support at both high flows and low flows. First off, I have no conflict of interest to disclose. Hope the presentation follows. Yeah, I have no conflict of interest to disclose, as I said, and we go right into the ECMO circuit, and you see that I think that there is not much to explain about that. You know that we are draining the blood from the inferior vena cava most of the times, right? Although from the venous system, this is pushed through a pump into the extracorporeal lung. The lung is oxygenating, decarboxylating, and the blood is returned to the systemic circulation. This very simple system is actually hiding lots of very interesting physiology for both the extracorporeal support and for the patient. I think that grossly we can divide the two systems. The title of the presentation is on low flow and high flow ECMO. Why is this important? Yeah, because I think the two systems, while there are let's say that there is a little difference, and for me actually the boundary is more or less 2 to 3 liters. More than 3 liters, we are for sure talking about a high flow system. Less than 2 liters per minute, we are talking about a low flow system, and then there is of course a gray zone in the middle. But why is this discrimination important? Well, because the high flow ECMO is able to provide oxygenation and the carboxylation very effectively, while the low flow ECMO is basically providing basically only CO2 removal, so the carboxylation. And while it seems only a matter of turning a knob, of course, there's a lot of implication for the patient. Let's only think about anticoagulation, invasiveness of the procedures, bigger cannulas, bigger or smaller cannulas, multiple puncturing sites. I think it's important to discriminate the two systems. But first, we need to talk about how oxygen and CO2 are transported in blood. And let's say with relatively simple standard parameters, let's talk about oxygen. And with these parameters, we have 16.8 milliliters of blood per 100 milliliters, oxygen per 100 milliliters of blood. Important is that we have 110 milliliters of mercury of PO2 and a saturation of 99%. Actually, everyone knows that hemoglobin is very important to dissolve oxygen into blood, and more than 95% of the oxygen is therefore bound to hemoglobin, and dissolved oxygen is very little. What happens then if we increase massively the PO2 with more or less the same saturation? Well, we have a little increase, quite modest increase in oxygen content, and we are basically increasing only the dissolved part. This is, I think, very important, because we are going to understand why we need to do certain actions when we are turning the knobs on the ECMO. This is very important. When the hemoglobin is fully saturated, there is not much more that we can do to increase the oxygen content, right? And when we talk about extracorporeal oxygenation, this is the relationship. The oxygen transfer is proportional to the extracorporeal blood flow, and also to the difference between the oxygen concentration entering into the lung and how much oxygen goes out from the extracorporeal lung. But as we said, that when the hemoglobin is fully saturated, the increase in oxygen content is not that much. That's why we understand it that if we want to oxygenate, we need flow. We need flow, because you can for sure increase the FiO2, but everything depends really deeply on the extracorporeal blood flow. That's why if we want to oxygenate, we need 3 or more liters. Is it the only factor? I think it's not the only factor. Of course, okay, we have blood flow. Minor part is the FiO2. Recirculation is also very important. And please, let's not forget hemoglobin. It makes no sense to run in my opinion, to run a patient with 6 of hemoglobin on ECMO, because if we want to achieve delivery of oxygen, then we need also to optimize the carrier of oxygen, that is hemoglobin. And about recirculation, we have quite interesting things to say. But first, about extracorporeal blood flow once more. It's not only about extracorporeal blood flow, right? Because the cardiac output of the patient does a role. And so it's very important to understand that this extracorporeal blood flow in comparison to the cardiac output. And you see that the Guaracin in this study, they did a quite simple thing, but quite important. They reduced with the beta blocker the cardiac output of the patient. And you see the heart rate goes down, the cardiac output goes down, and what happens is that the oxygenation increases. Why? Because the extracorporeal blood flow, let's say that our extracorporeal therapy is treating a higher percentage of the cardiac output of the patient. Let's remember that a big patient with a very high hyperdynamic circulation needs more extracorporeal blood flow to oxygenate it in the same way. This is known, but we tend to forget, I think, clinically. Recirculation, well, recirculation is easy to understand, but then very difficult to measure. The drainage canal sucks part of the blood that is returning to the system and is not allowing this blood to enter in the system in circulation. And with this simulation that I perform, you see that whatever is the saturation of oxygen entering in the extracorporeal lung, the more the recirculation, the more is reduced the extracorporeal oxygen transfer. So once more, the recirculation is an important factor that we need to keep in mind. And what is the easiest way to understand? It's difficult to measure, but what is the easiest way to understand if the patient isn't having recirculation? Yeah, well, I show you this video. I find this video very, very strange and very particular, and that's why I took it one night in our ICU. You see that the cannula is pulsating. Actually, it's not pulsating, but the blood is turning quite lighter with, I don't know with what, probably with a heart cycle. It means that the oxygenation of the blood of the cannula draining the blood is changing with the heart cycle. Very likely the recirculation in certain parts of the heart or the cardiac cycle is increasing, and that's why we get a higher saturation in the drainage cannula. So easy message. Check out the drainage cannula if you suspect the recirculation. Just check it out and address the problem. Maybe increase the distance between the cannulas. Okay. We talk about CO2. The transport of CO2 in the blood is quite complex, but we can make it relatively easy. The CO2 dissolves in the blood very much easier than the blood. That's why we don't need a carrier for CO2. But in the blood there is a lot of water. There's a lot of water, and CO2 also thanks to the carbonic anhydrases is transporting the blood mostly as a carbaminic compound and mostly as bicarbonate. So what our extracorporeal lung is able to remove is only the CO2 that is physically dissolved. Okay. And also thanks to the carbonic anhydrase, we are going to provide a lot of CO2 removal, but with a little amount of CO2 that is dissolved in the blood. And when we talk about the extracorporeal CO2 removal, well, we are talking about the surface of the membrane lung is one important factor. The sweep gas flow, you see that the more the sweep gas flow, the more the CO2 removal, the more the blood flow, the more the CO2 removal. And also the membrane lung surface clearly plays a role. So how do we maximize our CO2 removal? Well, theoretically, increasing sweep gas, increasing blood flow, increasing the membrane lung surface. But what is actually very interesting is that we should not forget that when we are doing CO2 removal in the natural lung, we are actually doing, we need a compartment with a high ventilation to perfusion ratio, right? When we need always to think about traditional physiology. And in our case, this is a high sweep gas flow for very little blood flow. And you see that in this study that we performed in Göttingen, we were able to achieve a massive CO2 removal, almost to the apneic oxygenation, only with 400 milliliters of blood. How? Basically increasing a lot the membrane lung surface and increasing a lot the VQ ratio. We had 15 liters of gas flow for only 400 milliliters per minute of blood flow. So now that we understood the physiology, now we don't need to ask ourselves, why do we do ECMO after all? And this is the first study from Zepo. The first, unfortunately, was a failure, technically massively complex in 1979. Here, the need was preserving oxygenation. I have to say that probably in the years we discovered Vili and ventilator-induced lung injury, and so everything changed. Now we have a problem that is always maintaining the gas exchange while protecting the lung. And these two things are deeply in contrast one to the other. So we use actually ECMO to try to make this contrast, this fight between lung protection and gas exchange a little bit more tolerable. And you see it on this editorial that we wrote a few years ago with Professor Gattino and Professor Quintel. You see that in the most recent studies, animal studies, big trials, Eolia, lifeguards, we were able to, thanks to ECMO, we were able to reduce deeply the invasiveness of mechanical ventilation, in this case measured by mechanical power. Respiratory rate, tidal volume, driving pressure, it's not important. We were able to reduce the invasiveness of the mechanical power or of the mechanical ventilation. This probably leads to a difference in outcome. There are very big discussions. I'm not going to dive into that of the Eolia trial, but there is a difference very likely difference between the treated group and the control group. Why? Because of the preservation of oxygenation as in Zepo study, very likely not, because you see that the PO2 is actually the same. What is actually very different is the minute ventilation of the two groups. So we are coming to the let's say to the new frontier of ECMO indication. That is probably no more preservation of oxygenation or gas exchange, but to the ECMO or Ingenix extracorporeal support allows us to disconnect, to unlink the gas exchange and the lung protection. So we performed actually a study on animals, and we wanted to see what happens in pigs when we are performing both during ARDS. So we performed a model of hydrochloric acid and oleic acid in different animals. We wanted to see what happens when we apply or ECMO or minimally invasive CO2 removal, because if the difference is not oxygenation, well, everything is played on the lung protection side, right? So let's see what we found. This is a very controlled setting, very difficult setting, but very controlled. You see that when we talk about, first, let's talk about oxygenation. What happens here? Yeah, well, you see what you actually expect to see, that for at least for some hours, then after there is probably the resolution of the damage, probably hypoxic vasoconstriction. Difficult to say, but the first 4 to 8 hours, the pigs treated with minimal invasive CO2 removal, so it means only CO2 removal and no oxygenation, they have a lower oxygen saturation, they have a lower PO2, and it's more they have a more profound hypoxemia. When after initiation of ECMO, we basically got 95, 96, 97% saturation, what we actually did not observe in CO2 removal. The group, that's clear. As these consequences, I think it does. We expected overall to achieve more or less the same CO2 removal with our setup between the pigs treated with the CO2 removal and with ECMO. Indeed, we achieved the absolute amount of CO2 removal. The same CO2 removal, we achieved it with both machines. The fact is that we were not able to maintain the same minute ventilation, and specifically the CO2 removal group had a much higher minute ventilation than the ECMO group. Or in other words, with the ECMO group, we were able to reduce the invasiveness of mechanical ventilation much more aggressively. Why is this? And this is, I think, a very interesting point. The total metabolism of the animals was massively different. And you see that in the CO2 removal group, the metabolism, the total oxygen consumption, and consequently the CO2 production were much higher, much higher. Why? We actually did not understand, because there are not many differences among the groups. What is clear is that those animals that were were actually not having let's say, perfect oxygenation, they were much more stressed. And this stress, this cellular stress, the overall stress led to a much higher oxygen consumption and CO2 production that prevented us to reduce deeply the ventilation. But this led to another consequence, that reduction of minute ventilation, despite we increased the PEEP, we maintained the same mean alveolar pressure, anyway led to a decrease in the lung compliance in the ECMO group. So the CO2 removal group, despite a much higher minute ventilation, maintained a better lung mechanics than the ECMO group. Something that we actually see every day in ICU. Patients enter an ECMO and very rapidly they tend to de-recruit. So we come to the final remarks. I think that whoever performs ECMO or inject extracorporeal therapy needs to have a deep understanding of physiology of CO2 and O2. The complete our study shows, I think, that the complete uncoupling between the gas exchange and the lung mechanics is actually hardly achievable when we decrease aggressively the mechanical ventilation, the invasiveness of mechanical ventilation. Then we observe a worsening of the lung mechanics. And this leads, after all, to the last question that we also asked a few years ago in our editorial on the Blue Journal. Should we balance rest and load when we start the ECMO? This is, I think, the question needs to be very fast addressed in future research about ECMO. Thank you very much.